This tutorial will show you how to use Bristol Nano Dynamics readback software. Following the previous tutorial, I have placed a shortcut to the installed application on the desktop. So we're going to double click this to open it. And you'll notice that many windows appear. I'll go through all of these windows and what they do once I've loaded up a file. To do this, we navigate to where the data has been saved. And you'll notice that in each folder that data has been saved in, you'll have a navigation image with the sample name and a .hsafm file. It's this .hsafm file that we want to drag into the playback window. This can only be done one file at a time. If you drag it and drop it anywhere in the playback window, the software will go through the file and identify the locations in the file of every frame. It will also load up the macro image, indicate whereabouts on the sample the data has been collected by a red crosshair, and load up the first frame of data. Going through the other windows, we have the frame plot. This is where the data is plotted that's been collected. The playback window controls which frame is being displayed, and there are different ways in which you can control this. You can either click play, and pause. You can select a particular frame number, or you can drag the frame indicator. This also displays the name of the current file that's being displayed, as well as the amount of time taken to collect the data on the top and the corresponding frame number on the bottom. Data has been collected using the vector microscope. As such, there is a macro navigation image shown here in the middle, which has a red crosshair showing where the current frame is. If we zoom in by clicking with the left mouse button, we can get it to display where all of the frames were collected. If I right click, display, auto scan, this shows you a red dot on the coordinates to the same resolution as the macro image, the locations of where each frame is collected. The blue line shows the path taken between the coordinates. You'll notice that this is also shown in the XY plot, where a blue cross is the location of a frame and the red cross shows the current location of the current frame. This sample in question was graphene on a copper foil, and this can be seen in more detail in the micro view. This image updates with every frame. Here I'm moving through the file by placing the cursor in the playback window on the frame number and using the up and down arrows. This moves one frame at a time, or I can place the cursor after the 10 unit and this moves 10 frames at a time. If you wish to zoom out of the macro image, right click, view, zoom to fit. Any metadata that was collected when the frame was collected can be shown in the metadata window under Other Info, or the cantilever, the imaging environment, or the experiment. The sample name was populated automatically when the sample was loaded. This is the version of software that was used to collect the data. The two key controls are the playback window and the construct window. I'll go through these in more detail momentarily. For now, if we look at the frame plot, there are some additional controls if you right-click. We can display a line profile through the data. Here you can see the red line profile line, cross-sections through the data, and the cross-section is displayed in a new window that has appeared. Here the cross-section goes from A to B, as indicated in both the frame plot and the cross-section window. Unless stated otherwise, all dimensions are in nanometers. We center the cursors, and then we can drag both cursor 1 and cursor 2 laterally to measure the dimensions of any of the nanostructures or microstructures present in the frame. If we find a frame which maybe has structures we wish to measure, such as this one, here we can measure the hole here, and we can see that the distance between the two cursors laterally is 566 nanometers. The measured depth, 12.7 nanometers. We close the cross-section by clicking on the cross. Other controls, if you right-click on the frame plot, enable you to export the frame in a range of file formats. These range from a formatted PNG to a Gwydion file. When you export in this fashion, a new folder is generated in the same folder that the original file was loaded from, called Single Frames. Here we can see the formatted PNG with lateral and vertical scale bars embedded, and also the Gwydion file. Gwydion can be used for additional sample analysis. You're also able to change the color scale I think we'll leave it on grayscale. Additional controls can be found in the tabs in the Construct window. I'll now go through these. The lateral tab at the top shows the current resolution, lateral resolution of the frame plot window. This can be decreased and increased. You'll notice that when this resolution is changed, the frame number resorts back to frame 0. When going through a file for rapidly trying to identify frames of interest, we would suggest that the medium resolution is selected. If you are exporting data for presentations, for further data analysis, we'd recommend that the high resolution is used. You can see the corresponding pixel sizes as you change resolutions changes. The plot control lets you select whether just slow scan trace or retrace or all data is plotted. The restart average is more relevant to the data collection software. The Plot tab lets you select what data is plotted in the vertical scale of the plot. To Depending on the data that was collected, some of these will not actually contain any data. I know, for example, this dataset only collected topography. When data is collected using our microscopes, it is collected in raw XYZ coordinates. These are then reconstructed into images using a range of flattening methods that are available. These are linear in X and Y, polynomial, this is a third order polynomial, median of differences, DC offset, or none. The exact flattening method selected will be dependent on the type of data that you wish to extract from your frames and the type of sample that you're imaging. A 2D plane subtraction can also be applied or removed from the data. The colour scale may also be changed from here as well. The Filters tab is for more advanced data processing, and I won't be covering that in this presentation. The Services tab has many different features, and I'll come on to this in one moment. The Advanced Setting tab lets you override many of the settings that were recorded when the data was collected, as well as additional controls for the 3D display. Back to the Services tab. The key ones that will be of interest will be the Show Stitching. This enables you to stitch the data into a composite image. Here we can clear a canvas if there is already data from previous stitching, and we can match the frame heights. This button here enables you to remove any DC offsets between overlapping regions of frames. This may be used for covering global sample slopes or very large objects as you move across them with multiple frames. To start stitching, simply click the Start Stitching button. You'll notice that the software moves through the file as well as having a progress bar for stitching. The resolution is initially low in the stitching canvas, but then moves to full resolution once the process has been completed. Here we can see the full stitch, with regions of graphene oxide and graphene. If we wish to export this, we can right-click in the stitched canvas plot, move to Export, and then select the format in which we want to export the data in. Depending on the size of the dataset, this can take some time. Here we are exporting a 3.7 megapixel image. In the same folder structure that the original file can be found in, a new folder called Stitch Frames has appeared, and you'll notice that the stitched file has been placed here. Again, with pre-formatted lateral and Z scales. We can close the stitching controls by selecting the Hide Stitching. If we wish to export multiple frames, we can move to the Export window. Here we can choose to export every frame in a file in multiple formats. For example, if I wish to export every frame as a Gwydion format file, I select Gwydion, I move to the start frame that I wish to start on, click Running Export, and then click Play. And now every frame that is being displayed is also being saved to the single frames folder. This process will continue until it reaches the end of the file, or up until the end frame number has been reached. However, it is important to turn off this setting, else it will keep exporting as you carry on other tasks throughout your analysis. Within the frame export window, you are also able to export videos. If we click on the video tab here, we can select the speed in terms of frame rate of the AVI that's generated. Here we can select a frame rate multiplier of 4 to our frame collection rate of 2. We can select that we wish to have a scale bar, and we click export and then play. Now any frames that are processed are now being formed into an AVI. I'll let this complete. Again, it's important to turn off this setting. This saves the file, but also stops you adding additional frames in with further processing tasks that you may be carrying out. Again, a new folder is generated called Video Exports. We hide the export window by clicking Hide Export. Show 3D Display opens up a 3D rendered view of the current data. You can navigate this 3D window by using the left mouse button to orbit, holding down Shift and the left mouse button, moving the mouse up and down to zoom in and out, holding down Control and the left mouse button to pan. You'll find further controls for the 3D display under Advanced Settings. These include a multiplier for increasing or decreasing the scale of the Z, or turning on or off specular highlight lighting. You find that the 3D rendering of the surfaces is very useful for people who are not used to looking at height color-coded topographic scanning probe microscope datasets. The 3D window can be closed by, again, in the Services tab, selecting Hide 3D Display. The nanomapping software will be covered in a future tutorial. If we click the Show Information, this collects information about the currently processed frame, such as 18 different types of surface roughness, but also any variances in time with these properties. For example, here we look at how the SA surface roughness measurement changes with time, from frame to frame. A histogram is also built up of this property. We also have the ability to plot in the Histogram of Values tab a histogram of all of the Z heights present in the current frame. In the same way to the cross-section, the cursors show you the lateral distance between them, and also, in this case, the vertical distance, which equates to the count number. I'm going to close the information window by clicking Hide Information. Frame stacking is used in situations where frames are collected at the same location to increase the signal to noise. This can be enabled and disabled using the button here. I'll show you it in process in this situation. However, because we were constantly moving in this frame set, this doesn't really make much physical sense. If you wish to close the readback software, We close it using the cross on the playback window. This has been a brief overview of the capabilities of the Bristol Nano Dynamics readback software.